Okay, we've made it to the last video for chapter 3. We're going to look at property trends within the periodic table. And like I said, we already identified chunks of the periodic table that are metals. That's going to be in kind of the purplish color. And then over here, we've got metalloids. That's kind of the stair-step region right here. And then we've got non-metals, which are usually in this far corner. And then hydrogen's the weird exception. All right, what I wanted to do was take you through a few examples of property trends within the periodic table. And the first thing I want to do is I want to take a look at these halogens right here. So halogens in this example, or I shouldn't say in this example, halogens are in group 7A. And if you use the international system, we would just say they're in group 17. But let's go ahead and take a look at what these look like in real life. So I'm going to go ahead and paste an image in here because I'm not very good at drawing. And we'll go ahead and we'll take a look at these halogens. So over here on the left, what I have is chlorine. So chlorine is this colorless yellow gas. It's diatomic, right? So it's going to be Cl2, meaning it's two chlorine atoms that are bonded together. And it's homoatomic, meaning it's two chlorine atoms that are identical bonded to one another, versus heteroatomic would mean different atoms. All right, so we've got chlorine, and then next over we have bromine. And if you remember in the last video, I said that bromine's kind of one of the weird nonmetals. Bromine's actually a liquid, so you can see it kind of pooling up in the bottom down there. But bromine, again, is diatomic. It's Br2. And it's homoatomic, meaning just two bromines, no other elements. And then over here, we've got iodine. Iodine is kind of this black, brown, purple solid, kind of depends on how you look at it, but it's I2. And if you heat up iodine, you actually get this weird purple gas that gets emitted off of it. So as you can see, they're all similar, meaning that they're all homoatomic. They're all diatomic as well. And they all have properties where they have at least some gas present. So in the chlorine one, you can tell there's a lot of gas, bromine a little less, and iodine a little less. And then chlorine over here doesn't really have any solid or liquid, and then we go to liquids, and then we go to solids. So yeah, there's some similarities, but as we kind of move down that group, their properties do change a little bit. So now here's my thought question for you. What about this last one over here? This last one is called statine. And this would, as we can imagine, be represented with the elemental symbol At. And if we were going to predict what this looks like and how it behaves, we could say, well, first things first, I would predict that it's going to be diatomic and homoatomic, just like the other ones, right? So I would predict it to be At2. And then if I were to predict the properties of it, I'd say, well, it seems like as we're going down the column, meaning we're getting to heavier and heavier halogens, that it's behaving less like a gas and more like a solid. So what I would do is I would just predict that it's going to be a solid metalloid. And in fact, it falls on that stair step, so we know that it is a metalloid, but it's going to start behaving less like a non-metal and more like a metal as it gets more and more solid-like. So we can predict some of these properties as we move down a column. So what this kind of brings me to is that within the same family or group, they may have different physical properties as you go up or down a column. So let's make a note of that. Elements in the same group, sorry about my messy handwriting, have similar chemical properties. Sorry. But they may vary up versus down a column. And let's kind of go back and review another one. It's one of my favorite ones, but this time rather than being a physical property, let's take a look at a chemical property. Whoops, let me slide this over. So this is actually from group 1A. So group 1A, and if you remember, these are called the alkali metals. And I'm actually going to blow this up so that it's a little bit bigger. And alkali metals will react with water. And as you saw in that Brainiac video, it gets more and more and more and more reactive. So if we go back to our periodic table, the alkali metals are over kind of in this region right here. We're going to ignore hydrogen right now because hydrogen we know isn't going to behave like a metal. So the one we have on the top is lithium. So let's go ahead and fill this in. You can see that lithium metal, when you put it into water, does a little fizzing. They didn't even bother showing it in the video because it's not super impressive. It's just kind of a quick pop. It generates some hydrogen gas. But then once you get to sodium, sodium gets a lot more reactive with water and alcohol, and will start producing more and more and more hydrogen gas. So it's a lot more vigorous because we're moving down the column. And then we can go to potassium. Potassium's way more vigorous. In fact, it's really hard to transport potassium. They actually have to store it and ship it in little oil vials to keep any chance of water getting in out. And then you can imagine, well, what about rubidium? Well, as you saw in the video from the as you saw in the previous video, this gets even more vigorous. So I'm just going to make a note, more vigorous. But as you can see, both chemical properties are going to be the same. All of them produce hydrogen, but the extent and rate at which they produce hydrogen gets more vigorous. Kind of like over here, we saw the same physical properties, but it got more extreme as we went up and down a column. All right, so that's one general idea I wanted to go over. And then last but not least, I want to take a look at some general trends. And in order to do this, I wanted to show you a quick image of what these atoms look like in terms of their size. And this is a little bit confusing, but basically what they've done, right here is they've chopped out where the D block would be. So I'm just going to say no D block. So over on this side right here, this is going to be my S block. Let me put my dash in there. And over on this side, I'm going to have my P block. All right, so they've just kind of chopped out that middle part of the periodic table, and they've altogether omitted the F block. But the S block and P block, if we look at it, we can notice some unique trends within them. So for example, if we go from left to right, you see how we're getting smaller? Lithium, even though it's a quote-unquote lower atomic element, is actually smaller than fluorine, which is kind of interesting. So it gets smaller radius left to right. So that's another unique trend. This time, rather than comparing columns, meaning groups or families, we're going to be comparing periods, so across the row. Oops, I've had two T's there. So smaller atomic radius left to right. And then in addition to that, let's go down a column here. If we go down a column, you see how we're also getting bigger as we go down a column? So we could say it gets bigger, radius, down a column. All right, so let's just kind of summarize this really quickly. So I, as a student, really love just making a quick little sketch of a table, and I'm going to say, this is my kind of unartsy attempt at a periodic table right here. And atomic size, we said, gets larger as we go this way. So atomic radius increases that way. So I would make this on my study guide, and then I would also say it increases as we go down. All right, So this trend is really helpful, especially as you get further and further along in chemistry. You can just say, well, it's to the left of this element, it must be a little bit bigger, just based on standard periodic trends. All right, there's also one other one I wanted to talk about, and this is called ionization energy. And then ionization energy is basically a measure of how much energy is needed to steal an electron. Does it take a lot of energy to steal an electron, or only a little bit of energy to steal an electron? Well, let's think about this, right? And if we think about our alkali metals, for example, let's go way back up. These alkali metals all have one electron in their last s orbital. Question is, do you think it'd be easy to steal that one electron? Yeah, I'd say so, because if you steal one electron, then they'll actually look like their noble gas electronic configuration. And we know that noble gases are really, really stable. So alkali metals are going to be far and away the most stable when you steal an electron. So let's go ahead and kind of zoom back down. And I'm going to do the same kind of unartsy periodic table. And I'm going to say the further we get to an alkali metal, the lower the ionization energy is. Versus if we imagine an element like a halogen over here, where it's one away from a noble gas right next to it, it doesn't want to lose an electron. In fact, it's much, much easier to gain one electron, because then it would have the electronic configuration of the nearest noble gas. If it were to lose an electron, it would have to lose all the way over until it started behaving more like a halogen in terms of its electronic configuration. So that's the first one. And then ionization energy as well. It's a lot easier to steal an electron from a big atom. Kind of think about it like a wealthy person, right? If you stole $1 from a wealthy person, they probably wouldn't even notice. Bill Gates has plenty of money. So the bigger the element is, the lower the ionization energy is. Not that I am telling anybody to steal from anybody, just to be clear. But these elements, when they're really, really big down in this corner, they have a massive electron cloud. If they lose one electron, yeah, they lost one, but in the grand scheme of things, they got plenty. So it doesn't take very much energy to steal an electron from a really big atom. So this is the other thing that's kind of nice, is you notice how both of these trends are exactly the same? There's a lower ionization energy for big atoms, whether that's left and right across the periodic table or up and down across a periodic table. So if you can remember one of these, you should be able to remember the other one. So let's really quickly imagine again, before we stop, what's going on in ionization energy. So let's say we have sodium. Sodium on the periodic table, if you remember, is kind of right here. It's in group 1A. And sodium, if it's going through this ionization energy, is going to lose an electron. So it's still going to be sodium. We haven't gained or lost any protons. But if we lose an electron, meaning we kick an electron off, what charge would this sodium have? Well, the fact that the electron that was lost had a negative charge, and we can't just create or lose charges, means that the sodium must have a positive charge. So sodium, in this case, becomes an ion, meaning it has a charge. That's why this is called ionization energy. It's basically saying what amount of energy is required to make a cation from the neutral element. In this case, sodium is really happy as a cation. In fact, table salt has sodium cations in it, so it's nice and happy in that form. All right, I hope that helps, but let me know if you have any questions.